All right, here we go into Unit 7. The first lesson is on exponential functions. All right, so all exponential functions have a few things in common. One, you'll notice they have this setup where they have an a times b, which is known as the base, raised to the x. Now, what you'll notice about exponential functions is the variable is in the exponent position. Okay, that's why we call these exponential functions. Every other function you've seen pretty much at this point has had the x in the base position, not the exponent position like you see here. Okay, so this is really what makes exponentials exponentials. All right, now here's an example. Y equals 4 to the x. Now, what I'm going to do is I'm going to start at 0 because if we plug 0 in, we've basically got 4 to the 0, and anything to the 0 power is 1. So basically 4 to the 0 becomes 1 and our output is 1. All right, so there's our first point. Now if we were to go backwards, all right, like -1, then we would have 4 to the -1, which is the same as 1 over 4 to the first. Well, 4 to the first is just 4. So really that's 1/4, or in decimal form, 0.25, 1/4, right? 25 cents. All right. And if you went further back, we would get an even smaller number, right? So 4 to the -2nd, which is 1 over 4 to the 2nd, or 1 over 16. So a really, really small number, which is fairly close to 0, all right, is what you would get if you plugged -2 in for x. Now, let's go the other way, and let's watch what happens to the y values as we increase x. So if we plug a 1 in for x, we have 4 to the first, which is just 4, okay? And then if we plug a 2 in for x, we have 4 to the 2nd, which is 16, all right? And if we plugged a 3 in, well, we'd be off the charts at 16 times 4, because that's 4 to the 3rd power, right? Because this is 4 squared. All right, which is 64. All right, so we'd be off the graph at that point. And what you can see over here to the right is the coordinates plotted on this graph. All right, but that's a basic exponential function. Let's see where we go from here. All right, so the first thing I want you to see is at the top of this slide, the exponential function with transformations. So I want you to notice where h is and where k is. H is on the x in the exponent position. So that would control, notice the negative is built in like you're used to seeing. That would control all horizontal shifting of the graph. All right, and then there's k, which is in that normal position, and it controls any vertical movement, any vertical shifting in the graph. All right, and then there's a. When a is bigger than 1, you're vertically stretching it, just like you have before. If a is negative, then we are reflecting it. If a is between 0 and 1, then it's a shrink, right? So all the same things that you've seen the last several units in a row apply here for this function, okay? Important information. When the base is greater than 1, when b is greater than 1, remember that this is your base, right? The graph will be an exponential growth function. So basically, from left to right, the function will grow. That's growth. That's what you want to see your bank account do over time, or the value of anything that you own. like your house. When the base is between 0 and 1, that's how you write a between, it will be an exponential decay function, okay? And there's lots of things that do this over time, but this is what an exponential decay function looks like. And if you think about the value of something decaying over time, basically we are approaching 0 on the y-axis, okay? So as we go to positive infinity, we approach a y value that is approximately 0, okay? So that's decay. It's like the value of your car over time generally depreciates because you keep using it, you know, year after year, and it's, you know, eventually is going to wear out, all right? Or the value of a lot of different things like computers and technology. There's exponential decay is generally what happens with most of those devices because they get used up. Battery dies, screens, technology gets outdated, faster programs can't run on slower devices, you know, etc., etc. All exponential functions will have a horizontal asymptote as part of the graph. An asymptote is basically an invisible barrier. I'll let you fill in the gaps here. An invisible line that cannot, it won't be touched or crossed. It's a value that the function approaches but never actually reaches as the function moves to perhaps positive infinity or negative infinity if it's a growth function. As we go left on the function, we might be we're approaching a certain value, right? The domain of an exponential function is all real numbers from negative infinity to positive infinity. And the range will depend on the k value, okay? Because the exponential growth and decay functions start at 0, but if we shift the entire graph up, it's whatever that k value is. Well, if it's growth, it'd be from k to positive infinity. If it's reflected, it might be flipped around. It might be negative infinity to k. If a is greater than 0, we're fine. If a is less than 0, then it would be from negative infinity to k. And I put a bracket around that, and that is wrong. Because what's going to happen is we're going to be approaching that k value, but you're not actually going to be reaching the k value. Okay? So, again, that has to do with the asymptote. The asymptote is at y equals k. All right? All right. All right. You've got 3 exponential functions all graphed on the same graph here so that you can kind of compare each of them together. So, you know, you start with y equals 2 to the x, and then the base increases to 3. And what happens is the function gets steeper quicker. That's one way to look at it. There's other words you might be able to insert in there, but you notice it increases in value a lot quicker. Steeper is a word I like to use with this. It gets taller quicker. I mean, it just, you know, the rate of change goes up. The rate of change in y goes up. So we're increasing in value substantially quicker. All right. All right, so I'm going to do this one for everybody. There are no transformations on this one. We don't really have there's no a value. The a value is equal to 1. Okay. The h is 0, and the k is 0. So no transformations. So the asymptote, remember I said, was at y equals k. So y equals 0, since k is 0. The domain is going to be from negative infinity to positive infinity. And I know you don't see it yet, but the range is going to start at 0. It's not going to go below the x-axis, but it's going to go to positive infinity. All right. So we're going to do a t-table here for this, x, y. Okay. And I'm going to plug in 0. And remember, 2 to the 0 is, anything to the 0 is 1. If I plug in a 1, I have 2 to the first, which is 2. If I plug a 2 in, 2 to the second is 4. If I plug a 3 in, 2 to the third is 8. And if I plug a negative 1 in, 2 to the negative 1 is 1 over 2 to the first, or 1/2. Okay, so if I plot these points, I've got 0, 1. I'm going to go backwards to negative 1/2. And, you know, negative 2 is going to be a quarter, and then an 8, and then a 16th, and so on and so forth. It gets really close to 0, basically, but it never gets to 0. As I go to the right, it's going to be 2. And then if I go to 2, it's going to be 4. And if I go again, it's going to be all the way up here at 8. And there's the graph. Exponential growth. Hopefully you noticed that, because b is greater than 1. And since a is 1, it's not reflected. It's just going off to positive infinity as we go right. As we go left, we are approaching k. We are approaching 0. Okay? That's not k divided by 0. We're approaching k, which is equal to 0. But we never actually get to 0. The graph never actually hits 0. Which is, again, why we put the parentheses around the 0 in the range. Okay? It gets really, really close to 0, but never actually gets to 0. All right, I think that's it.